So today we're going to continue our conversation about the normal distribution and use it to calculate the probability. Well, first, what is this use for our learning objectives? We're going to use the normal distribution to calculate the probability of random variables, normally distributed random variables, right? So the random variables follow a normal distribution, and we'll use that distribution to calculate the probability of values. And we can kind of inverse that, and we can calculate the value of a normally distributed random variable based on a probability, a percentile, right? Like the 95th percentile, 95% of observations fall below this, or a cumulative probability. So that's kind of the inverse, and we'll talk about how to do that, of course. But you can imagine, I want you to calculate the example from that video is our heights. And so it's like, well, what is the height associated with the 95th percentile, right? 95% of people are shorter than this height. And so that's the inverse problem that we would calculate. Okay, so let's look at that normal distribution again. And we're going to think about, we've got our mean right here in the middle. And we're going to think about the percentage or probability of observations that fall certain standard deviations away from the mean. So there's one standard deviation, right? Oh, let's just draw that. And I'm drawing these fairly arbitrarily, but they would be symmetrical. So that's 1 sigma. And then we can think about 2 sigmas. And then we can go all the way to 3 sigmas. And the idea of kind of using sigma as this metric, how many sigmas, how many standard deviations are you away from the mean? That can give us some information about how extreme an observation is. And the nice thing about the normal distribution is this thing called the empirical rule. Empirical just means something that we observe, and we can observe with the standard deviation, or sorry, with the normal distribution, that if we go 1 sigma away from the mean, that accounts for 68% approximately of observations. And we can write that another way: 68% of observations fall within 1 standard deviation of the mean. And I'll just shade that in. So this is 1 standard deviation of the mean on either side, right? So that's 68%, or 0.68 if we think about it in terms of probability. If we go out to 2 sigma, we account for 95%. And then 3 sigma, we account for 99.7%. So that's all the way out here. That's the vast majority of observations in this case fall within 3 standard deviations. That's called the empirical rule. So that's a kind of a property of the normal distribution. Now let's review the standard normal variate, which we calculated last time and we defined. Remember, this is called the z-score. In your book, it's denoted as S, which no one else uses. So we're going to ignore that. And z is equal to some value x minus the mean divided by the standard deviation. This is just a way to standardize any value. This is whatever value of our random variable. If it's a height, it's 5'11", right? It's just some value. And by standardizing it and calculating this z-score, what we're doing is this ends up being the way to interpret this z-score is the number of standard deviations away from the mean. And we can use this to compare z-scores among different populations. And so we'll look at an example of that. What's another special property of the z-score, the standard normal variate? Z follows what kind of distribution? It's a normal distribution, but what are the parameters of that? And the mean of z is 0, and the standard deviation is 1, right? And so if I get a z-score of 1.5, I plug in some value for x, I use the mean, the standard deviation, then this means I'm 1.5 standard deviations away from the mean. It tells you basically how extreme an observation is. A low z-score is something close to the mean, a high z-score is something far away from the mean. So in that video, the against all odds video, if you got to look at it, if you don't, you'll learn this. They gave us this funny example of the Boston Beanstalks Club. And this is a club for tall people, basically to get together and meet and date. Because it's hard for tall people to date. And what they found was the kind of observation of this club was that, well, of course, the gentlemen are typically taller than the ladies. But let's look at the actual distribution of heights. And so I think these data are for kind of just national statistics. So we'll just say US adult female heights. They follow normal distribution with a mean of 63.8 inches and a standard deviation of 4.2. And then male heights. Again, normally distributed with a mean of 69.4 and a standard deviation of 4.7. And then the rule that kind of like, whatever, the rule for this club was that ladies can join if they are 5'10" or taller, which is 70 inches. And men can join. Freudian slip there. Men can join if their height is greater than or equal to 6'2", which would be 74 inches. Yeah. Just in by the wire there. So we can ask some questions of this. Is this height requirement fair? And what does it mean by fair? Yeah, and how would we compare that?
Well, I know that the average height for a girl is 5'4", so you have to be 6 inches taller than average. I think the average for a guy is 5'8", so that would be 6 inches too.
Yeah, so how, basically you're saying, how far away are you from the mean? How extreme or far away from the mean? Are these benchmarks, we'll say. And that way we can compare them. Are they both 95 percentile? Are they not? Are they different, right? Because that would be a way to kind of compare. Obviously, it's not, are they the mean or not? So to do this, to compare this, we can use the z-score. How extreme these values are. All right, so let's calculate the z-score, and we're going to do z for females. And that is equal to 70 inches minus our mean, which is 63.8, divided by the standard deviation, 4.2. And then z male is equal to 74 minus 69.4 all over 4.7. So now we get a z-score. The z-score for the ladies is 1.48. The z-score for the males is 0.98. And we can interpret this as 1.48 sigma from the mean, right? And 0.98 sigma from the mean. And I'll draw that out for you. Each distribution is going to be different, right? So the ladies will be centered around the mean of 63.8. And then what we're saying is you have to be 70 inches, which is over here. And this is 1.48 sigma from that mean. So, and then the males would be, over here, right? But on a different distribution, because it's just a different distribution has a different mean and a different standard deviation. So what do we find? Is it fair? Is it the same? So you have to be taller, quote unquote, as a lady from the distribution of the ladies' heights to enter this club. Why would that be? There's no like statistical reason for this. I think it just came down to I think taller women had a harder time finding a partner, and so they made a different. Oh yeah, it's more restrictive. So maybe it's the other way. I don't know. I think they set those thresholds because they wanted to have even numbers of men and women coming, and so apparently there were more. it was harder for guys, I guess. That's probably what it was. I don't know.
That seems weird. That seems like backwards.
Yeah, I don't know. I'm not part of this club, but I'm sure there was a reason, and maybe this is outdated. Maybe, you know, those videos were pretty old, right? From the 80s. So maybe in 2022, the rules have changed a little bit. Yeah. Okay, so now we can ask another question. Let's calculate the percent of US females and males eligible for this club based on that normal distribution. And we have the z-score, right? So this is something that we can use. We don't have to calculate the z-score to do this. We could just base it on each normal distribution. But now that we have the z-score, we can use this function phi of z. And do you remember what this tells us from our last lecture from last week? What is phi of z? If we plug in a z-score into this function, this was the CDF of the normal distribution. Yeah, so if you calculate a cumulative distribution value, that gives you the cumulative probability, or the probability that in this, or whatever our random variable is less than or equal to that value z. Or kind of the z that we calculated, right? So cumulative probability, or otherwise known as percentile. And so what we're going to do is plug those z values in, and then we can use our table, or we can use R to calculate this. So table A1 in your book. We'll look at the table here that we have on Canvas. So first we'll do the ladies. So we're going to do phi of z female is equal to phi of 1.48. And then let's pull that table up. So the way this table works, we're here on page 2. So we're above the mean because we have a positive z value. Over here, we have negative z values. And we're going to calculate the cumulative probability, or the CDF function, the area under the curve up to that z value. So 1.4, and then we're going to go across to 8. 1.48, so 93, we'll just say 93%. So this means that 93% of observations or of female heights fall below that. And so 7% are eligible. And then we'll do phi of male. Go back to that table. 0.98, so 0.98, 83.6, we'll say 84%. And then we get 16% of males are eligible. So we did the inverse there, right? First we calculate the z-score, how extreme are the observations, and then we use that to calculate a percentile associated with that. Okay, so now what we're going to do is prove to ourselves how that empirical rule works. And take out your activity guide, and I'll pull it up here on Canvas. So what you have here is a graph with the normal distribution, the standard normal distribution, right? So it's centered on 0. And we have Z on the x-axis. They committed a faux pas. They did not label their y-axis. I'm very disappointed. Always label your axes. Come on. Okay. But it says the standard normal density curve. So we know we have probability density here. So what do you think if we were to count the area of these squares? What would the area be? 1. Okay. So first thing we're going to do is estimate the number of rectangles that fit under this curve. The area of any density curve is 1. And so that will represent the proportion, 100% of the data, right? So here we have, maybe you can say this is 1 right here if you add these two up. And then just kind of, the way I would do this is just say, okay, is it greater than half? Is it half or more of a square? Count that as 1, and then ignore everything that's less than half. And then that'll probably give you the number. So start counting that. That's the first step that we'll do. And then we're going to go and use the empirical rule to figure out the proportion of observations within different standard deviations. Okay, so we got about, I got about 40, 42. So we'll just say 40 to low 40, something like that. So whatever that is, just write that down. Of course, this is going to be approximate, right? Now, the next thing we'll do is, so we'll say we have about 40, 42 squares right there. Now we're going to divide this up and find the proportion of values that fall above and below the 0 mark, or the number, right? Just count that very quickly. Obviously, we know that's going to be 50%. And then what you'll do is at the end, there's this table at the very back. And so just once you get those values from the squares that you count, put the proportion in there. So if there's 42 squares and you count 20, divide 20 by 42 and put that estimated amount. And then based on the Z table, so based on this Z table or the one in your book, put the actual value that it should be based on the theoretical normal distribution, okay? And I can give that to you. Of course, 0 is going to be 50%, 50% is on either side. 1 is 84%. Or sorry, that is 84% is all the way up to 1. So you're going to want 1, let's see here. Let's go back to that. Okay. Yeah, I guess you can so we're gonna do 0, we're going to do -1, -2, and then everything's symmetrical, so you can kind of just repeat what that is. So up to 1 is 84%, right? But then what you can do to prove it to yourself is what is the area between 1 and -1, right? And that should be what follows the empirical rule.
For part C right there, what's the percentage?
Just compare them. I mean, this is just an exercise to kind of familiarize yourself with how this all works. What I would like you to do though is this, they didn't set the table up this way, but what you're doing is you're calculating you're going from -2, -1, 0, 1, and 2. And you're calculating these areas up to these points, right? And you really only have to do one side because each side is going to be symmetrical. So these are our z values right here. And then what I want you to do is calculate the proportion of area within plus or minus 1 and 2 z, which is also standard deviation. And then compare this with the empirical rule. That's ultimately what I'm interested in having you do. Does that make sense? Okay. So yeah, you don't necessarily have to do all those little steps in between, but if you finish the first -2, -1, 0, and then you should be able to calculate those empirical rule values. So the empirical rule would be this is plus or minus 1, and then plus or minus 2c. And that should approximate, if we go back to our notes, it should be about 68%. And then that should be about 95%.